Heat is a common form of energy in chemical reactions, so we're going to investigate the heat concept just a little bit in this chapter. We will have to use the information that we learn in this chapter in a future chapter. So again, heat is energy. I do want to distinguish that heat is not the same as temperature. One thing you can do on the next slide, we'll learn about the units, and you'll see that the units for heat and temperature are different. So sometimes that can help jog your memory that they're not the same thing. I think the reason that we often think of them as interchangeable is because temperature is a reflection of the energy or the heat. So they are connected, and oftentimes we follow heat by measuring the temperature of things. So they are connected, but they're different. So heat measures the total energy. Okay, so heat is energy. Temperature, which is really reflecting how hot and cold, temperature, is measuring the kinetic energy of the particles, which is the energy of the motion of the particles. And so temperature reflects that energy of how they're moving. Now, another difference between heat and temperature is energy. Heat does depend on the amount of the substance, where temperature does not depend on the amount of the substance. And the illustration that helps me kind of get that into my head is if I had a small beaker of water, and let's say it's on a hot plate and I have 50 milliliters of water and I'm heating it up. Okay, so let's heat it up. And if I'm measuring the temperature, once it starts boiling, it would be 100 degrees Celsius, right? If at that same time I take a larger beaker, and now let's say I have 500 milliliters of water, and I'm going to heat it up, and I'm measuring the temperature that it boils, it's still going to boil at 100 degrees Celsius, right? The temperature of that boiling water is independent or does not depend on how much water is present. However, just from your experiences at home, the amount of energy that it is required to heat 50 mils is going to be less than the amount of energy that it takes to heat 500 mils to boiling point. The more water you have, the more energy it takes to reach that boiling point temperature. So the energy does depend on how much substance is present, whereas the temperature does not depend on the amount of substance that's present. So let's look at units for heat. So we know, just as a review from a previous video, temperature has metric units of Celsius. We also have the absolute zero scale, Kelvin. English units that we can use is Fahrenheit. So those are units for temperature. The units of energy that we will encounter are joules, which has the abbreviation of a capital J, and calories, which has the abbreviation of lowercase c and then AL. Now, I always think of food when I think of calories. We call that a nutritional calorie. interestingly enough, a nutritional calorie actually is not identical to the calories that we'll be talking about. A nutritional calorie, the name has a capital C and the abbreviation has a capital C. Like there, you can see. And the relationship between the two is a nutritional calorie is 1,000 of the lowercase c calories, or 1 kilocalorie. So we'll be working not in nutritional calories when we see them, but nutritional calories are a form of energy, but they are 1,000 of the little calories that we'll be talking about. And if you look on a label of any type of nutritional label and they list the calories, you will see that they use a capital C for the calories. It's not an accident, it's the unit. Whoops, I think, okay. So I need to insert a slide here that I'm missing. All right, I had to insert a slide that I missed. So another thing that it's a physical property that we need to talk about when we're talking about heat in terms of what we need to know is something called the specific heat. And every substance has what we call heat capacity, just like every substance has a density. So heat capacity is a physical property of the substance. And what the heat capacity tells us is how much energy that particular substance will absorb before the temperature changes, or how much energy it needs to absorb to have the temperature change. So you can see right here the definition of specific heat capacity. It's the amount of heat, which is energy, required to change 1 gram of substance 1 degree Celsius. And so the units that we use are associated with that definition, right? It's the unit for energy, so it could be calories as well, over the gram, so it's 1 gram by 1 degree. So the mass and the temperature. And so that's our units for specific heat. Now, why I make it emphasize the units for specific heat is now we have several things that we're going to be using in an equation that are different properties, but kind of can easily get mixed with each other. We know we have temperature, which for our time being, we'll just use the metric degrees Celsius. We have heat, which can be joules or calories. And now we have specific heat, which is going to be joules, grams, degrees Celsius. Or if you have calories, it would be calories, grams, degrees Celsius. So it's important, I think, to help you answer the questions that you're asked, to know the units associated with each property, because then it makes it easier to read the word problems and to know where each thing goes, if you know what unit goes with what property. Now, before we leave specific heat and see some examples, specific heat, which is a constant for specific substances, the larger that value is, what it tells us is that it takes more heat to raise the temperature. So the larger it is, the more energy that is required to raise the temperature. So let's look at some examples. So here, this is from my other text, but it's just some common examples of specific heats. There's the first column is the substance. The next two, the middle and the one on the right, are both specific heats. The difference is the one in the middle has heat units of joules, and the one on the right uses heat units of calories. So they're both specific heats. Now, what you'll notice is water is at the top of this list, and it has a very high specific heat. Water is very good at absorbing energy before it starts to change temperature. So it can absorb a lot of energy before it heats up. That's one of the reasons that water is used commonly as a coolant, because it's a coolant's job to absorb energy and keep machinery cool. And so water does a good job at absorbing that energy and not heating up quickly. Notice at the bottom of the chart are all metals, and they have relatively low specific heats. Then they're not all identical. Aluminum is the highest of the ones listed, but compared to things like water, they have pretty low specific heats. I mean, look at lead, 0.128. So that's how much energy it was absorbed before it changed 1 degree Celsius. I often think, just practically, this is why when you have metal, like a metal park bench or your automobile, when it sits in the sun for a long time, it gets really hot, because metals doesn't take much energy for them to change their temperatures. Now, there's no numbers on this slide that you would need to memorize. If you are asked to do a calculation and the specific heat is needed, it will either be provided in the question, or you can go and look it up, the specific heat for the particular substance that you're working with. So you don't have to memorize these specific heats. As far as specific heats, you need to know the definition, the units, and that the larger the value, the more energy it will absorb before it changes temperature. So what we're going to do is calculations with specific heat, and there's an equation. And we will use this equation now as we kind of introduce ourselves to the idea of a heat concept. And then in a future chapter, we will come back to this equation and have to use it together with a different equation. So in the middle here, I've written it with the symbols. So Q is heat, M is mass, C is the specific heat, and delta T is the change in temperature. So a change in temperature, that delta is change, just means we take the final temperature and subtract the initial temperature. Now, if this number is negative for what we're doing, you can just take the difference. You can put the positive value in. For changes in temperature, a negative value just means that heat was lost. So the temperature went down. A positive value just means heat was gained. And so the temperature went up. So for the equations and calculations we're doing, we really just need the difference between the two temperatures. We won't have to be determining if heat is lost or gained in that way, but that is the difference. So if you have a negative temperature, that ends up with a negative heat, and a negative heat just means that energy was lost. It's not an actual negative number, like less than 0. So let's look, I have 2 problems, and let's just take a look at how we would use this information to solve a problem. So the first one just says how much heat is needed to raise the temperature of 200 grams of water from 22.5 to 77.3 degrees Celsius. All right, so if you want to pause and try to see if you can solve this this problem by using this equation that we just talked about, you can try to solve it first, and then you can come back, start the video again, and then I'm going to go ahead and work through the problem. All right, so this is the equation we need. Q is heat. Right? So they're asking me how much heat, so I need to find Q. So that means if I am finding Q, that's what I'm looking for, all the other values must be given. So I need to know the mass. So there's the mass, that's M. Specific heat, I need to know this is a constant for the substance, and they told me it was water, and they did not give it to me in this problem, but if I go back to my table, the specific heat is 4.184. I'm going to work in joules. Okay, so I know that. All right, so I know the specific heat, and then the change in temperature I can do here. So it's going to be 77.3 minus 22.5, and that's degrees Celsius. So let me get my calculator. So it's 77.3 minus 22.5. And I get 54.8 degrees C. Okay, so I know all the numbers I need. So the heat equals the mass times the specific heat times the change in temperature, which I already subtracted over there, so I have the change in temperature. Okay, you know I like units, so if I look at my units, I see grams cancels, temperature cancels, and so I have joules, which makes sense because that's the unit for heat. So this is pretty straightforward. I'm going to say 200 times 4.184, which is a specific heat, times 54.8. And I get, my calculator needs some new batteries. Okay, I get oops, I don't want pink here, sorry. I get 458.56.64 joules. I'm going to double check because my calculator is looking very sad right now. Okay, let me see if I can, come on, let's see, 4, 5, 6, 8, 9, okay, let me try one. Okay, I'm going to pause and I got to look at my calculator. Okay, I confirmed with my calculator. It was giving me a little bit of trouble. Yeah, see, I'm not immune to that either. All right, so that's the answer to my calculator. Now, we always want to try to report in significant figures. So when you're multiplying and dividing values, you need to look at measurements. You need to look back and see which has the fewest significant figures, because that is what will determine. So our mass has 3 sig figs. Our constant here, our water, this has 4. And then we already had some sig figs here because when we subtract, we kept the 1 past the decimal, but this has 3 sig figs. So 3 sig figs seems to be a good amount of significant figures, an appropriate amount. So you could write this value in standard notation or in scientific notation. I'm going to keep the first 3 digits. So it's going to be 4, 5. I'm dropping off a 5, so this will round up to 9. Then remember to keep the 2 zeros, but since the decimal is all the way here, we have to keep those zeros as placeholders. Don't put a decimal place. Or we can write this in scientific notation, which would be 4.59 times 10 to the 4th joules. So either way for me would be acceptable, has both units, has significant figures. Sometimes in the homework they're specific, but as far as the exam or for what I'm looking at, either of those would be okay. All right. So let's try a second type of problem that doesn't ask us for heat, but asks us to find one of the other variables in the equation. So this says calculate the specific heat. Okay, so not the heat. It wants us to calculate the specific heat of an unknown. If 1638 joules raises the temperature of 125 grams from 25 degrees to 52.6 degrees Celsius. They don't tell us what it is. It's an unknown substance, and we're trying to calculate the property of specific heat. So the equation you're going to use is Q equals mc delta T. In this situation, it is C that is the specific heat. So if you want to, you can pause the video and try to use the question and solve for C. And then you can unpause the video and watch me work it through and see if we come up with the same answer. Okay, so hopefully you've already worked it, but if not, here we go. So again, if I see calculate the specific heat, I would write down the equation. I know I want to find C. So that means everything else is given. So this number right here is going to be Q. It doesn't tell me that it's the heat, but I know that it has joules, which is units for heat. So that's my Q. So 1638 joules equals, I need to know my mass. It doesn't say mass, but I know that grams is mass. So I have 125, so this is M, grams. Now I don't know C. And then a change in temperature. So it does tell me my change in temperature. This also increases in temperature. I worked with another student and theirs decreased temperature, so they got a negative value here. In what we're doing, all that means is the temperature decreased. You may make it just take the absolute value, the difference of it, to solve this problem. So 52.6 minus 25.0 is 27.6. Now there's a variety of ways to simplify this. What I'm going to do is I'm going to multiply these two numbers together. Since they're on the same side and they're two numbers, I can multiply. Remember, units multiply and divide just like numbers. So 125 times 26.7, and I get 3450. Oops, let me go back to my black marker. The units now are joules times degrees Celsius, and then I still don't know C, and this is still the same. Then to solve for C, I get it by itself. I'm going to divide the 3450 over to the other side. So I get 1638 joules divided by 3450. And if you solve the problem without watching me and you get the same answer, it's fine. Sometimes once we've been doing algebra for a while, you might have a slightly different approach to how you're going to rearrange, which is okay. Multiplying and dividing allow that. And so then I get in my calculator, when I divide those two numbers, 0.47478. It keeps going. The units are appropriate for specific heat. It's joules over grams degrees Celsius. You can see those units right there. That's always a good sign when your units match up. Now, significant figures. Let's see. I see my heat. Go back to what your measurements. This has 4. My mass has 3. And my temperature has 3. My temperature change has 3. So 3 would be appropriate. So I'm going to cut it off here. So then to report my answer, I'll say 0.47. Because I'm dropping off a 7, I'm going to round up to 5. And so that would be my specific heat. Now, just so you know, if you go back to this, I didn't spin, sorry. So just keep in mind 0.475. And if we go back to this, what we can see is that is probably, it would be a good guess, that unknown substance is iron because it has a specific heat that is very close to iron. And I say that only that we have a limited list here. If you knew all the specific heats, there's probably more than iron that has close to that, but it would be a good guess given the information we know. So I'm going to say, is this iron? Question mark. So from this video, you need to try to understand the heat concept, that heat's energy common in chemical reactions, that heat is different than temperature, even though temperature kind of reflects properties of heat. They are two different things. Know the units for temperature and for heat, and know how to use the equation, the heat equals mass times specific heat times change in temperature, to solve problems similar to the last two problems that we did.